Hi everyone, welcome to part 2 of lesson 6.1 on confidence intervals. Thanks for joining me today on yet another snow day in the state of North Carolina. You'll need your handout from yesterday. We're going to pick up where we left off. There is an activity related, but I think we're going to wait and hold off and do that when we're together, just so we can discuss it like I would prefer that we would. So we're just going to continue with the notes instead, okay? So where we left off on your handout should be on the second page of your handout underneath the dotted line where it says confidence interval for a population mean. And you'll need to have your calculators handy and I think your textbook as well, okay? Let me scroll through and get to where we need to be. This is all the stuff we did yesterday. There we go. Okay. So remember we started talking about confidence and really talking about, well, how close, and how assured do we want to be that the population parameter is going to fall within a certain range. And that's really, that range itself is a confidence interval. So a confidence interval is a range of values constructed from sample data that we would have collected so that a parameter occurs within that range at a pre-selected probability. And as you're going to see today, there are certain standard pre-selected probabilities, okay? Technically you could use anything, but there are 3 in particular that are most common. That pre-selected probability is what we refer to as the level of confidence. So you'll be hearing these phrases as we go through. So a couple things to note. In most of our examples, the population parameter is going to be a mean value, mu, but it doesn't really have to be. It could be a population proportion, p. You will see that once in a while. It could even be maybe the standard deviation itself that is the parameter of interest, or really anything else. But for the most part, what we're going to see largely is using the population mean mu. So as we've seen with other things, there are definitely conditions that need to be met in order to be able to create a confidence interval and be assured of the validity of that interval. So the 3 conditions that need to be met. First and foremost, we need a simple random sample. Typically, we're going to assume we have one, and it would, of course, be of a certain size n. We need to know that the normality condition is met. Now, if the population distribution is normal itself, so, as we've seen before with the central limit theorem and what we learned in Unit 5, if the population itself is normal, you can be assured that the sampling distribution will be normal as well. If the population distribution is not normal, remember that the central limit theorem tells us that the sampling distribution will be approximately normal, provided we have a large enough sample n. And usually when we say large enough, usually over 30. That's actually a standard kind of measurement. So when we say big enough, 5 is not usually big enough. Usually over 30 is a good number, okay? And the last condition is the independence requirement. This would be of the individual observations themselves. It's required for use, of course, of the standard deviation formula. Remember that sigma over square root of n formula. And along with that goes the fact that the population needs to be at least 10 times as large as the sample. So it's almost like some of the things we talked about before tying into the independence itself. So now the interesting part, the fun part. This is actually pretty good. It's good math, so you'll need your calculators. It also revisits some of the stuff we've seen before with normal curves, so It's very much rooted in stuff you have seen before. Okay, so keep that in mind as we go through that. So to get a confidence interval, and we usually refer to a specified confidence interval with capital C. All right, and what we want to do, through that confidence interval is be able to catch the central probability under the normal curve. So how do you think we could do that? And figure out the number really, on the number or on the normal curve that occurs. Well, think of a normal curve. Z-scores. Everything always comes back to z-scores. All right, but when we're typically talking in relation to confidence interval, you're going to see us use the notation like z star, okay? You'll see why in a minute, okay? But we usually designate it that way. But technically it's a z-score, okay? But specifically in relation to confidence intervals, we'll often denote it as z star. All right, so what we're going to do is work through a few, different levels of confidence and talk about, okay, how do we figure out where that's going to occur on a normal curve? Kind of like where is that, sweet spot? Where is that cutoff? That's going to tell us, okay, we can be 95% certain our mean is going to fall in here, in this range. How do you figure out where that range goes? That's really what we're talking about. So I think, oh yeah, these are on your third page. I have these all set up for you. Glad I remembered to do that. All right, so we're going to start with a 95% confidence interval. CI, remember, is confidence interval. So suppose we wanted to catch, or wanted a 95% confidence interval, meaning we need to capture the central 95% of the area under the curve. All right, so let's go ahead and mark off our units just like we always do. So of course we know in the middle is mu. Here's going to be like 1 standard deviation, 2 standard deviations, 3 standard deviations. Like we're used to. Oh, that's -1. All right, and if we want to catch 95% of the area under the curve, well, remember the empirical rule does tell us that 95% of the data is going to lie within 2 standard deviations. Remember that's only an estimate though, okay? As you're about to see, it doesn't come out really exactly 2. You're going to see it's a little bit off. All right, so maybe if I put markers here, okay, that means I'd have 95% of the data caught in between these 2 markers. Okay. Well, as we've talked about before, well, if there's 95% in the middle, obviously that leaves 5% left over for the tails, meaning that tail and this tail. But that 95% is split between the two, or the 5% rather, is split between the two. So that leaves like 2.5%. All right. So if we think in terms of probabilities, because that's really what the area under a curve is a probability. So think of this left tail, 2.5% as a decimal, of course, is going to be 0.025. All right, so together they make up that 5%. So what we want to do is, knowing what those tail areas are, is there a way we can figure out where this and this, and they are symmetrical by the way, can we figure out where that falls? Hopefully you're thinking inverse normal on your calculator. Because that's really what you're doing. Remember, with inverse norm, we used that when we knew the area under the curve, which we know here, it's 0.025, and we wanted to find the z-score. All right, so let's go to our calculators. And inverse norm, remember that's going to be under second vars, third one down, area is 0.025, and we are talking z-scores, so we're going to keep mu as 0 and sigma as 1. So it's about negative 1.96. Now remember what I said about the empirical rule? Empirical rule tells us 95% of all of our data falls within 2 standard deviations. Remember, that's pretty much just a guideline, an approximation. This is more accurate. It's not really 2 standard deviations. It's really 1.96 standard deviations. No, it's darn close to 2, but it's not exactly 2. So this is a little bit more accurate. All right, so remember that number, negative 1.96. So if we go back, what we now know is this z star is a negative 1.96. All right, that's this right there. All right, this one here, that's a positive 1.96. Now remember, if you wanted to do that on your calculator, remember inverse norm, it's always the area to the left. So if you wanted to find that positive 1.96, you'd have to do the 95% plus 2.5%, like all that stuff to the left, and then you'll get the positive 1.96. All right, so you have to remember things like that we talked about before. All right, so you need to remember this number, 1.96. All right, because what we refer to this 1.96 as, it's a critical number, or critical value, whatever you want to refer to it as. Now that's specifically, though, for a 95% confidence interval. All right, those of you who have had calculus know it's not like critical numbers in calculus, okay? Just coincidence, it's a similar name, okay? So this 1.96 really becomes what we refer to as a critical value when we're dealing with a 95% confidence interval. The reason we call it that is this is the number that we're going to use for any 95% confidence interval at all. It's never going to change. Doesn't matter what the story or the scenario is. If it's a 95% confidence interval you need to create, this is the number you're going to need to do it. All right, and I haven't showed you the formula yet that you'll be using this number in, okay? But you need to know the number. All right, so you'll notice that you have some more graphs. We're going to go ahead and do the same exact thing for a 90% confidence interval and then a 99% confidence interval. All right, so we're going to go through the same exact thing. So let's mark off our graph. All right, so if it's a 90% confidence interval, now we want 90% of the data to be caught in the middle. All right, so we want 90% here in the middle. So it's not going to be as much as 95%, so we're not going to go out as far as 2 standard deviations. So maybe I'm just going to kind of call it right around, like maybe in between, like here maybe. All right, so we're going to go through the exact same process we did before. All right, so if we have 90% caught in the middle, that leaves 10% left over between the 2 tails. So if there's 10% left over, obviously there has to be 5% in each tail. So 0.05 is the area. All right, so what we want to find is the z star that goes with that. All right, so once again we can use our inverse normal. Let's go back to the calculator. All right, so second vars. And this time our area is going to be 0.05. And we can leave 0 and 1 as the mean and the standard deviation. And we get approximately negative 1.645 will make it. So remember that number. And again, they're symmetrical. All right, so this 1.645, that's the critical value for a 90% confidence interval. All right, and again, these are going to become values that you'll probably have memorized sooner than later. Or you could easily find them. You don't necessarily have to memorize them. You can kind of just find them like we are doing now. But this becomes a value that's going to work its way into the formula to actually find what the confidence interval is. Okay, so we got one more to do. A 99% confidence interval. All right, so if we're talking catching 99%, we're talking almost everything. Remember again the empirical rule that 99.7% of the data is going to fall within 3 standard deviations. So we only went 99%, not 99.7%. So it's probably not going to go out quite as far as 3 standard deviations away. But it's probably going to be close. So maybe I'll just call it like kind of like right here. Right, so this is 99% in the middle. Again, if we got 99% in the middle, that leaves 1% left over. So cut that in half. So that means our tail area is a 0.005. All right, so we want to find the Z star that goes like right there and right here. All right, so we can do that on our calculator again. .005 and keep 0 and 1 and negative 2.576. Remember that. So this is a positive 2.576. So again, this 2.576, that becomes our critical number when specifically we're talking a 99% confidence interval. All right, so I think I have this table on your handout as well at the bottom of your 3rd page, and it's really just to summarize what we did. All right, so if we have a 90% confidence interval, meaning we want to catch 90% within that interval that we're going to generate, the area in the tail was going to be 0.05. The Z star we found was 1.645. So as I said, chances are pretty good. You'll probably have these numbers memorized before too long. But worst case scenario, okay, if you forget what they are, because you'll see soon where you need them, because you really will need them. Worst case scenario, you can figure them out by doing what we just did. All right, figuring, okay, if it's a 90%, I got 90% in the middle, leaves 10% left over, so the tail area is 0.05. And just do inverse norm to figure it out. All right, so worst case scenario, that's what you can always do. All right, if it was a 95% confidence interval, remember that the tail area was 0.025. And the Z star number we had for that was 1.96. And finally, a 99% confidence interval, the tail area is 0.005, and our Z star was 2.576. All right, so remember what it is we're trying to get at. We're trying to find an interval, a range, in which we can specify how confident we want to be that the population parameter really truly is going to fall in that region. All right, that's what we're trying to do. Okay, so keep that in mind as we move forward. All right, so how do we actually go about finding this confidence interval? All right, well, the first thing you're going to have to do is identify your population of interest and the parameter that you want to draw conclusions about. And I can't spell, obviously. All right, so when we're talking about the parameter, it's probably going to be mu. Maybe it could be a proportion p. It's typically, I think more of what you're going to see right now are means, okay? You're going to have to check the conditions for your procedure. They're the three things we talked about before: the simple random sample, the normality condition, and the independence requirement. Okay, that's what we're referring to there. All right, then you'll actually do your calculations. All right, so the first thing you'll have to decide is how confident do you want to be? Really confident, in which you might do like a 99% confidence level. Not so much. Maybe you'll do like a 90% then, or maybe even lower. And that's really going to determine, that's the question that needs to be answered. A lot of times you'll be told what to use, but if you're not, you pick one. Doesn't matter. Even on the AP exam, there'll be times where they don't tell you what confidence interval to use. You can pick anything you want. And you can make that determination yourself as to how confident you want to be. All right, the next thing you'll have to do is, if you actually have data, perhaps in a list on your calculator, you'll need to calculate your sample mean, your X bar. All right, now sometimes they'll just give it to you, okay? But if it's actually data that you have to work with, you might have to put it into a list, run your single variable statistics, and get X bar, okay? That becomes like your center for your confidence interval. Okay, if you remember that simulation we did yesterday, remember the red dot that was in every confidence interval, and I said that's your mean from your sample. Okay, so your X bar becomes really the starting point from which the confidence interval is going to be created. The next thing you're going to do is find your standard deviation of the sampling distribution. So that's where we're going to use that good old formula we're used to doing. That is back again. All right, so if you start thinking about what you have numerically, you have your X bar, you got a standard deviation, and by definition, remember, standard deviation is how far you are from the mean on average. Okay, so it kind of makes sense that sort of works its way into this confidence interval calculating. All right, so now comes the formula part. So the unknown population mean mu is contained between X bar minus Z star times sigma over square root of n, and X bar plus Z star times sigma over square root of n. All right, so think about why that makes sense. We're choosing a confidence interval, so I'm just going to pretend 95%, okay? So we can be 95% that our observed mean is going to take on, remember that, all right, go back to the central limit theorem. Remember that it should be true that the mean of our sampling distribution should be the same as the population mean. Well, if that's true, they're kind of interchangeable. So if we used our X bar as a starting point, the same should be true. That could be a mu. All right, because in theory, by the central limit theorem, they should be the same. All right, so they're almost interchangeable. So think about what this is. All right, you're starting at X bar, or think of it as mu on your curve if you prefer. Going to the left, you're going to subtract away Z star, that's that critical number you found, times the standard deviation over square root of n. All right, so in doing that, what you're coming up with is the z-star is telling you how far, you can go away from the mean. And then the standard deviation is what you multiply by it. All right, and that's how you get your confidence interval. So once you get the hang of it, the math is actually pretty easy. And students generally do very well with these. Yes, of course, your calculator does them for you, which we will be doing in a minute. All right, but we are going to practice doing them by hand first. So that's how you get your confidence interval. And we can conclude that we are like C% confident that the true population parameter, the mean, lies between blah and blah. The estimate of the unknown mu is x bar, and the margin of error is really going to be that z star times sigma over square root of n. So if by chance they ever ask you for a margin of error, it's going to be that z star times sigma over square root of n part. And then you interpret your results, which we'll be talking about. That's the part we were mentioning yesterday. There's definitely a certain way to interpret them. Okay. All right, so let's try a few practice problems. We are almost done. And along the way, we're going to be talking about how you can do this in your calculator as well. Okay? So the first one we're going to start with, I think it's just an example of finding a z-star number. It's number 10.7 on page 632. Now they want us to use the table, like the z-score table. We can just use our calculator because I know that's what you generally prefer. You want a confidence level of 97.5%. So we want a 97.5% confidence interval. All right, they're purposely giving you weird ones to make you think and do the math. So we're going to draw a picture just like we did before and figure it out that way. All right, so if we want a 97.5% confidence interval, let's draw ourselves a normal curve. U is in the middle, so 1, 2, 3. One, 2, 3. So if we want 97.5% caught in the middle, you could really put it anywhere as an estimate. I like to think through it because I know like 95%. Remember, empirical rule, lie within 2 standard deviations. So this is 97.5%. So it's probably going to be a little past like 2, like maybe right around here. And well, I really can't. I'm drawing very lopsided curves these days. All right, so this would be 97.5% in the middle. All right, so we have to figure out how much we have left over. So if we did 100% minus 97.5%, what's that, 2.5%? All right, so we have to cut that in half because that's going to be our tail area. So 0.025 divided by 2, we get 0.0125. All right, so this tail area here, this has an area, a probability of 0.0125. All right, so this is where we're going to do inverse norm, so let's go back to that. Let me clear out some of the stuff. So second vars, third one, so 0.0125, and leave those the same. And all they're asking us to do is find that critical number. So our answer is, and now the critical number generally is the positive version. All right, so in this case, we'd have a z-star of 2.241. All right, so that would be like this right here. All right, and that's our critical number. So it's very much, a lot like what we did before. We just didn't call them confidence intervals before. All right, let's try number 9. So this one's a little bit longer. So we're analyzing pharmaceuticals. So if you read the paragraph there, you might want to pause this and take a minute to read it. What they tell us in there is they give us a bunch of information. Apparently they're doing a study about if the amount of a certain type of ingredient in a drug they're making. So they tell us that, let's see, in all the information, if you sift through all this stuff, thought they told us what N was. Oh, there it is. Okay. If you can't, I'm sorry, I'm looking at the one you're going to have for homework. I apologize. Number 10.9 is the one we're doing, the one on the IQ scores. So, and this was 31 7th grade girls. So N is 31. I'm sorry, I was looking at the homework one you're going to have. And you can see they have all 31 scores there. Okay. They're treating this as a simple random sample of all 7th grade girls in the school district. Assume that the standard deviation is 15. And the first thing they want us to do is construct and interpret a 99% confidence interval. Okay, and we're going to go through all the formal steps involved in doing that. Okay, so you can see exactly what it looks like. Okay, you'll notice they reference this inference toolbox. That's pretty much the stuff we said you need to go through. Okay, so if you think about the first step, all right, go back to your steps. We had to identify the population of interest and the parameter. So the parameter, well, you have to figure out, is it a mean mu or a proportion p? Well, it sounds like we're talking mean, probably the mean IQ score is my guess. All right, so our parameter is going to be mu, and that's going to represent the mean IQ of all 7th grade girls in the school district. So notice in stating that, we have the parameter. We also have the population of interest. Our population is all the 7th grade girls in the district. All right, now let's think about the conditions that need to be true. All right, the first one, remember, we had to have a simple random sample. Well, they tell us we have one. All right, so that's easy. All right, second one was normality. All right, and remember that this is the issue that, okay, if we know the population is originally normal or approximately normal, we can be assured our sampling distribution is as well. They don't really tell us anything about that in here. Sometimes they will, but they don't here. So really all we have to go on is the idea from the central limit theorem that tells us if n is large enough, the sampling distribution should be approximately normal. All right, and remember in this case we had an n equals 31. Remember me mentioning 30 is often considered like big enough? So we have 31, so we're good. All right, and the final one is independence. And remember, that's the independence of one observation over another. So in this case, I think I forgot some letters in here. In this case, we're talking the girl's IQ score. So I think it's pretty safe to say that the IQ of one girl is independent of the IQ of another. Right, and there are the conditions that can be met. So now that we've done all that, now we can actually find the confidence interval. Right, and this is where we're going to use that formula, and I'm going to show you one way to set it up. Okay, so remember we wanted a 99% confidence interval. That's what they specified here. All right, and remember how the formula goes. Remember, we're going to start with our x bar, and remember you're going to go to the left and then to the right. So we can kind of like condense it and do like plus or minus notation. And remember how the formula goes. It's going to be z star times sigma over square root of n. Yes, a formula you should memorize. I'm pretty sure they give it to you on the formula sheet though, but you might want to memorize it. All right, x bar. We need that. We haven't figured it out. We would basically have to put this list of numbers, all 31 IQ scores, into a list, run one variable statistics, and figure out what x bar is. Okay, I already did that, so I will tell you what we got. It was 105.839. All right, so the way I got that was I just put all these numbers in a list, all 31, and then did one variable statistics to find the mean. All right, then plus or minus. Now this is where you need that critical number for a 99% confidence interval. All right, so go back to the table. With a 99% confidence interval, our z star number is going to be that 2.576. And then that's going to be times sigma, which is 15, over square root of 31. Okay. All right, so now we actually have to find the interval. Now remember, it's an interval, and hopefully you know interval notation from Algebra 2 and pre-calculus. So yes, it's in parentheses. If it's not an interval. So yes, it must be in parentheses. All right, so let's go to our calculator. We'll talk about easy ways to type this in. All right, so let me clear this out. So we got 105.839. All right, now we typically do the value to the left first, so we're going to do a minus first. All right, and this is where we need 2.576 times 15 divided by square root of 31. Make sure you come outside and hit your right arrow to come outside the square root, or else it might not put the parentheses in the right place. All right, so hit enter, and that will be your left endpoint. All right, so 98.9, I guess you could just make it if you want. All right, so let me go back really quick. So 98.9. Okay, so that's my left endpoint. Now, trick. You don't have to retype all this. Remember, you can do second enter, and that will pull up the entire line, and then you can just backtrack with your left arrow. Go change that minus sign to a plus. Saves you a heck of a lot of time, and I overshot it. Come back. So just change it to a plus right there. Keep everything else the same. There's your right hand endpoint. So like 112.78. And that's your confidence interval. Now they did want us to interpret it. All right, and this is what I've been talking about. There's definitely a certain way to interpret it. Yes, it's something you can pretty much memorize and fill in the blanks. So this is how it goes. We can be 99% confident because we're doing a 99% confidence interval. So we can be 99% confident that the true mean IQ score of all 7th grade girls in the district lies between, so 98.9. If there were units of measurement, we would attach them here. And that's your answer. All right, so think about what that means. That's telling us that, you know, we can be pretty darn sure that the true mean IQ of all the 7th grade girls is going to lie within this range. All right, so letter B. If these girls had actually come from one teacher's class within the school district, how would your work in Part A have changed? All right, so think maybe of the conditions. Would any of them be called into question? Probably the independence. Because if you're looking at all kids in the same class, you know, that means they learn the same way. You know, they might be taught to read critically the same way. You know, so it would be sort of a bad model for collecting your data, basically. All right, now since we've now calculated one of these by hand, okay, let's talk about how you can do these in your calculator. For our purposes, when we take our quiz and test, yes, I'm going to want you to write out the formula. That's pretty much the same on the AP exam as well. Okay, they like to see the formula, but it's certainly fine to do the rest of the crunching in your calculator and let that generate your interval. Okay, so let's switch back to the calculator and I'll show you where you do that. Let me clear this stuff. So where you're going to go is hit the stats button and across to tests. Okay, we haven't been here before. The one we want is the one that you see, the last one there in the screen. It's the one that says Z interval. That's your classic confidence interval. Okay, you're going to notice if you scroll down the list, you'll notice a few of them say interval. They're all different types of confidence intervals. All right, so your classic normal basic one is this number 7, Z interval. All right, and you'll notice a few different options. The first line of input, if by chance you had, like we did here, we had all those numbers in a list, you can enter them just that you have the data itself, okay? And when you do that, let me see, let me hit enter, there you go. If you happen to have the data in a list, you can let the calculator do all the work. Notice the third line there asks you what list is your data in. Okay, now on this one, I kind of told you what the value was, so if you go over to stats, this is where you can just fill in the information you're given. All right, so in this case, remember what was sigma? Sigma was 15. Let's do 15 here. X bar, remember I gave you that. That was the 105.889. Oh, no, 0.839, sorry. And N was 30. 31. And we want a 99% confidence interval. You can type that in either as plain 99 or 0.99. It will take it either way. It will give you the right answer either way. All right, so you really can do either one. It doesn't matter, okay? Just for your reference for later on. All right, so go down to calculate, and voila, there's the exact same thing we got. All right, really what the calculator's doing is using that exact same identical formula that we did by hand. That's how it's getting this. All right, so we're going to look at one more, and then we'll call it a day, okay? Let me go back. This is going to be... Oh, there's the part on how to do it on the calculator. Now, if you forget the keystrokes, I do have them in Brain Honey, okay? It's one of the very first documents in Module 6 for Unit 6, okay? So you can definitely look those up if you need it. So the last one we're going to wrap up today with is number 10.11 on page 633. Right, it's very similar to the last one, okay? So you get a little bit more practice. So surveying hotel managers. So a study of the career paths of hotel general managers sent questionnaires to a simple random sample of hotels belonging to major U.S. chains. There were 114 responses. So N is 114. The average time these 114 general managers had spent with their current company was 11.78. So since we're talking specifically about those 114 managers, that's our X bar. Okay. All right, so letter A. Construct and interpret a 99% confidence interval for the mean number of years general managers of major hotel chains have spent with their current company. And they do finally add there what the standard deviation should be. It should be 3.2 years. All right. So we're going to go through the same steps. So the very first thing is we need to identify our parameter. It sounds like we're dealing with means in this case. All right, so mu is going to represent the mean time spent by general managers at their current hotel, like job, chain, whatever. Okay. All right, so then we need the conditions. Well, simple random sample, they tell us we have one. All right, the second thing, normality. So let's see, do they tell us anything in there about it being normally distributed? Nope. So that's out. But if we use the fact that, okay, well, we don't know, this is again getting like, sort of like we did in the last one. Back here. If the N is large enough, the sampling distribution should be approximately normal. And what is it in this case? N is 114, so I think we're good. So central limit theorem, given large N Sampling distribution, I'm running out of room, that's why. Should be approximately normal. And then finally the independence issue. Well, I think it's fair to say, you know, how long one guy stays, or young lady, how long one person stays at their hotel is independent of another one. Okay, so there are your three criteria. So now we can actually do the problem. All right, so we wanted a 99% confidence interval. So remember how the formula goes. All right, so X bar was 11.78 plus or minus. Okay, this is where we need the Z star that goes with a 99% interval. That's going to be that 2.576. So 15 over, 3.2, where 15 was the last one. So 3.2 over square root 114. All right, so let's go ahead and do that, and then we can also take a look at it, you know, using the calculator features. Okay, so let me do it the long way. So we had 11.78 minus the 2.576 times sigma, which is 3.2, divided by square root of 114. And hopefully you got the same thing I got. So like 11.01 maybe we can make it. All right, so let's go get the other one. So remember, you can just do second enter and then backtrack with your left arrow to get back to change the minus sign to a plus sign. Now I want to change this to a plus. There we go. All right, so hopefully you got 12.55, 552. All right, so let's go ahead and do that with the calculator features. Remember, it's second, no, just hit stats and across to test. It's number 7. Didn't do that right. Tests. Oh, I didn't go to tests. All right, so it is statistics we have. Standard deviation's 3.2. X bar, that's our 11.78. And N was 114. Confidence level was 99%, so we can leave that like it is. And there it is. All right, so let's go ahead and interpret it. We're just about finished. All right, so remember, it was a 99% confidence interval, so we can be 99% confident that the true mean time spent by general managers at their current hotel chain. Is it chain or company? All right, I'll just put company. Lies between, and this is where you fill in the blanks. So this should be years. So it's like 11.01 years to 12.552 years. All right, so if you compare this with the previous answer, you'll notice there's some similarities. Notice how it's, pretty much it always starts out the same. And then where it goes from there is the true, mean. Now, if it's a proportion, you'll have proportion. Notice this part here is the statement of your population. And then finally, you just wrap up with your actual numbers. Okay? So there definitely is a pattern to how you want to answer this. All right, so then we just have part B, and then we're done. So the questionnaires were actually mailed to 160 hotels. Remember, it said they only got 141 back. How might this additional information affect your work in part A? Probably it's going to affect the conditions, because now you have non-response issues to deal with. You could figure, let's see, so it sent out 160 and 114 replied. So we could figure out what that is. I think it's like 71.25%, which I guess isn't bad. At least it's definitely more than half. But I think you'd have some non-response issues that could be affecting this somehow inadvertently. I'm trying to think of what other one. Definitely non-response. It really is a voluntary type of survey in which they're participating. So for part B, it could be kind of messed up if there's found to be some kind of, if something's wrong, bias built into the survey. Okay? So that should give you enough to do the homework, and I think that's plenty for today. There's only 3 problems. I'll just put them right here. And they're all like the ones we just did. So it's pages 632 to 633. It's numbers 10.8, 10.10, and 10.12. So just if you would do those 3, I'll be in touch about if I need for you to send me pictures depending upon what happens tomorrow, Friday. I have to sleep on that one. I don't know yet. Okay. But this is so remember you had the 2 problems from last night, 10.2 and 10.4, and now you have these 3. Okay. So we'll play it by ear to see if I see you on Friday. Otherwise, definitely check your email and I'll be back in touch. Thanks so much for taking the time to join me today. Hope you're having a good day. Stay safe, stay warm, and hopefully I'll see you soon.